Okay, so today we're gonna try, we're gonna start, we're gonna look at one topic, and then we're probably gonna start working on the second one, but probably will not finish it today. So first thing we're gonna do today is the phase plane or state space representation. So if you took a controls class, this is basically what you use all the time. All right, so let us consider the undamped system, which is the one we've been doing all the time. We have here K and M. Okay, so I'm not going to redo the derivation because we have done it already twice. So the equation of motion for this type of, for that system or any type of single degree of freedom, you can always write under the form x double dot plus omega n square x equal to 0, where omega n is the natural frequency, is equal to the square root of k over m. Okay, so we did that the last class. The solution of this equation can be written under the form x of t equal to the amplitude of sine omega and t minus a phase angle phi. Okay, so that means that we can rewrite that equation here actually as x of t divided by amplitude would just be equal to sine omega and t minus phi. Okay, and let's take this one as our equation letter A. Okay, so if you remember, maybe from controls, to work on the phase plane or state space representation, instead of working on the time domain, you work on the frequency domain, no? Okay, that's basically the idea. So think over here that omega is actually frequency, no? It's natural frequency. All right. So we have x0 deformation. If we want to find the velocity, v, that will be equal to what? Dx dt. Okay, so this will be equal actually to what? So will be equal to the amplitude. Now we differentiate with respect to t, so omega sub n cosine omega and t minus phi. Okay, and we know that the velocity can also be written as x dot So I can rewrite here that x dot divided by the amplitude times the natural frequency would just be equal to cosine omega t minus phi. And this could be our equation B. Okay, or here we can say, or above equation can be written as y over amplitude equal to cosine omega and t minus phi, where y would just be what? Would just be x dot over omega n. Okay, and let's say this will also be equation B, okay? Because it's the same equation, just write it in a different form. Okay, so really all the reason I'm doing this is to come up with what we're gonna do next. Here is that basically just to show that now if we add and square A and B, so basically we're going to do A squared plus B squared. That would be equal to what? So A would just be x divided by amplitude square, okay, according to equation A, because x, and y, if you want y actually, if you want, you can add here the y of t, if you want to make it just to look exactly as the same form, and the one will be plus y over amplitude square, and this would just be equal to, let's see, so A is sine, so we'll have sine square omega nt minus phi plus cosine square omega nt minus phi. Okay, and we know that this term over here is cosine square plus sine square, so it should be equal to 1. But at the end, what do we have? We're gonna have just this term over here will be x 1 square over amplitude square plus y square over amplitude square equal to 1. Actually, we did this. I mean, we talked about this yesterday. No, yesterday, the other day. And basically, what is kind of the figure that I did on last course is that to show that the solution is like going around the circle, no? It's the same thing. So now if you look at this equation here, what is this equation here? This is the equation of a circle, no? Or radius 1. So which is equation of a circle. All right, and you could actually move this one to the other side, no? The amplitude. So we could say equation of a circle of amplitude amp squared, no? Or amp. All right, let's just do it that way. So basically, all this is just to show that if we plot, all right, it's going to be difficult, that if you plot x over y, where y is the x dot divided by omega sub n. Okay, so be careful, my figure might not be that good. Basically, you have a circle, and what would be the amplitude or the radius of the circle should be the amplitude, no? So this is a equation of a circle of radius, the amplitude of the formation. Okay, so this is a perfect circle, but if you plot instead, did I do too much here? No. If you plot x over only the velocity, x dot, instead of getting a circle, we just get some type of an ellipse. Where the amplitude here will be on the x will be equal to the amplitude, but the y would just be equal to the amplitude omega n. Okay, this is what is known as the phase plane or state space representation. Okay, so why am I doing this? So remember, this is for this type of system, undamped system. So now we're going to study damped system, but the reason I'm doing this is because now it will be easy to observe that if you have a system that is undamped, but this is x, and let's say this is x dot over omega n. All right. So this means that the motion is continuous. So it starts here, you go through one cycle, you come here, you go through one cycle, you go from here, no? Now, what happened? So this will represent this. Forever and ever. Now, what's going to happen if the system has damping? Okay, so let's say viscous damping. So this time, slowly, the amplitude is going to go down, no? So we needed to represent that using the circle. How will it look like? So we start maybe from here, and then what's going to happen? It might go down, and then down, until it will go 0, and it will go like a spiral, no? Does that make sense? Okay, so that's the only reason, because once we start solving the equation, sometimes we're going to do this type of plot, and it's important that you understand what's happening. Okay, so the faster this curve goes to the center, the higher is the damping. The lower it goes in, the lower is the damping, no? Okay, all right. All right, so now let's see if we have time to finish this part. I don't think so, but we're gonna try. So, 31, free vibration with damping. Okay, so free vibration basically means that there's no external force. Basically, I mean, I will show it means that the differential equation is homogeneous. All right, so consider the below system. So this time we still have our spring, but we're also going to have a damper. And it's going to be considered to be a viscous damper. So this will be connected, let's say, to a block. Right, this way, and if you want, maybe I did too much here, but it doesn't matter. Let's do it this way. So it will be a block of mass M, spring of stiffness K, and for damping, generally the letter C is used. Okay, and in this case, so this is, oops, no, yeah, this is the ground. And to simplify the equation, let's say this is a smooth surface. Okay, so first thing to do is to derive the equation of motion. Okay, we know there's basically two steps. Step number one, we need to do some type of figure free body diagram, no? So we're going to do the figure of the block here. And you know we do two sides because one side will be for the forces, the other side will be for the inertia effects, basically the effects due to the motion. All right, so first thing we need to decide, it's a free body diagram, we need to select some type of reference frame. So let's say this will be X. Now, what will be the forces acting on that block? So you will have, let's say first the horizontal, let's first look at, for the vertical, sorry. We have gravity and G, and the normal force. And then initially, let's say we move this block a little bit to the right. So what are you gonna have? You're gonna have the force of the spring that will be equal to Kx. And now, if this is a viscous damper, what do we derive? We say that the force of the damper will always be a constant, so a value c, and that one should be proportional to what? Should be proportional to the velocity. Okay? So we know the velocity can be written as x dot, and this is always the case. The value of c might be take different values, but it's always the case for viscous damping. So let's say here, let me add viscous damping constant. All right. And now, okay, what type of motion is this going to have? Just translation. This will be equal to MA or MX double dot. So you see, step one, we do the figure. You want one figure or free body diagram, call it whatever you want. Step two would be to write down the kinetic equation, which in our case would be what? Summation of forces equals to MA. So in this case, the motion of the object is translation. So we only need summation of force equals to MA. In what direction is the motion? It's only on the x. So let's say we just apply summation of forces on the x equal to m. So it will be mx double dot. So what are the forces on the x direction? Everything comes from the figure, will be minus kx minus cx dot will be equal to mx double dot. Same thing as before. Okay, so we can just rewrite that equation as mx double dot plus cx dot plus kx equal to 0. Okay, and this will be the equation, so differential equation of motion for free damp system. So the term free basically means that the right-hand side is equal to 0. Okay? So again, now I could divide everything by m. So you will have x double dot plus c over m, cx dot plus k over mx, and k over m will be omega m, no? All right? So can't write it this form yet. But we can do it later, all right? So let's keep this form over here. All right, so now we need to solve that differential equation, okay? And see what would be the difference with the one before. Let's see, 29, all right. Okay, so we need to find the solution. And solution to mx double dot plus cx dot plus kx equal to 0. And again, it's going to be the same procedure as before. So what is the first thing we need to do? Is to assume harmonic solution. Okay, so over here, be careful with the notation. So basically, our harmonic solution is going to be x of t is going to be equal to C bar, not C, this is C bar. So this is a constant exponential of minus lambda t. Is the same thing that we had before, okay? But here, C bar is just a constant. Okay, so now that we assume the harmonic solution, what do we need to replace over here? We need to replace x, but also we're going to have x dot and x double dot. So let's see, what will be x dot? X dot of t will be equal to minus lambda c bar exponential of minus lambda t. And what will be x double dot of t will be equal to lambda square c bar exponential of minus lambda t. Okay, what is step 2 all the time? All the time the same thing, there's 3 steps, so will be step 2. Substitute into differential equation of motion. So what we need to do is to substitute over here. So that would be mx double dot plus cx dot plus kx equal to 0. So this will give what? So we'll have here m. Then we'll have lambda square c minus lambda t plus c of minus lambda c bar exponential minus lambda t plus k of c bar exponential minus lambda t equal to 0. Okay, we can factor out the c bar exponential minus lambda t. So we're gonna have over here n lambda square minus c lambda plus k equal to 0. All right, so as before, now we need to see when this equation is satisfied. So the above equation is satisfied. And here this means if and only if. I did on the previous notes, I just write I two F's, means if and only if. So what would be the two cases? If C bar exponential minus lambda t is equal to 0, which in that case, this yield to what is known the trivial solution. Okay, and the second case will be when m lambda square minus c lambda plus k equal to 0. So like I said before, this is known as the characteristic equation. But in this case, this equation here is of what form? This is a quadratic equation in lambda, no? Okay, so a quadratic equation in lambda, okay? And you know this, the solution of this will be equal to what? Will be equal lambda 1, 2 should be equal to what? C plus minus C squared minus 4mk. If you remember, this is of the form a x squared plus b x plus cx will be, this will be c plus minus, this will be actually b, no? B plus minus b squared minus 4ac, no? Okay, and here will be divided by 2a, which in this case our a is m, so will be divided by 2m. Okay, so let's see if I have space here to put it over here. I want to do it on the next page. So here, if we now put the values, we'll have lambda 1, 2 should be equal to, we can simplify that equation as, so the first term should be c over to m plus minus this one here we can, okay, we can write this as c over to m. If we put the 2m inside the square root, we need to square it, no? Okay. And now this term over here, this 2m becomes 4m squared, or 4m. So the 4m will cancel out, and we are left over here with minus k over m. Okay, so let's see, that would be page 32. All right, so now we know the two values of lambda. In order to find the solution, we can go back and substitute into the assumed harmonic solution, which is this equation. All right, so substituting, same process as before, as we did for the undone. What happens is that there's a lot more algebra in this case. So substituting lambda 1 and lambda 2 into, you can put assumed solution or into harmonic solution, it doesn't matter. What do we have? So the assumed solution is x of t equal to c bar exponential of minus lambda t. So here, be careful because it's going to become, I don't know, this marker is too thick. All right, so I don't know if it's going to be that clear. I'm trying to zoom in. So we have over here x of t will be equal to, you know what, I'm going to write it in a simpler form, will be c1 exponential of minus lambda 1t, let me put it that way, plus C2 exponential of minus lambda 2t. Where lambda 1 will be equal to C over 2m. So we have these two roots over here. All right. So let's take the positive one first. Plus C over 2m squared minus K over m. And lambda 2 would just be the same thing, but with a minus sign, C over 2m minus square root of C over 2m squared minus Km. Okay, so this will be our general solution. Okay, so lambda 1, lambda 2 are these two constants, and C1 and C2 are constants to be determined from initial conditions. There we go. All right, so next, let us rewrite the solution x of t under a different form. Okay, so in order to do that, we need to define something known as the critical damping constant. And we're going to call that one C sub C. Okay, so the critical damping constant is defined as the value of the damping for which this term over here become 0. Okay, so we have C over 2m squared minus K over m equals 0. So the value of C, for which this is equal to 0, which corresponds here to this term, is called the critical damping constant. All right, so in that case, if you want, this was C is equal to C sub C. So let's put here C sub C. Okay, so we solve this. What are we gonna get? So let's see, we could get, let's solve it, C sub C square over 4m square equal to K over M. We go to the next page. So it means C of C squared is equal to 4m squared K over M. Okay, and if you remember, oops, sorry for that. You remember omega n squared is equal to K over M. So what we're gonna have at the end, that C sub C will be equal to 2m omega sub n, because this term here is omega n squared. So this is what is known as the critical damping constant. Okay, so let me magnify out a little bit. We're not done yet. Huh? So now we're going to define another thing. There's another thing called the damping ratio. And it's given by the letter C in Greek. Okay, so the damping ratio is defined as, and this is just a definition, Xc will be equal to the damping constant divided by the critical damping constant. Okay, and here what is nice is that this damping constant will always be lower than 1. For our case application will always be between 0 and 1, but actually there is something that exists, such as negative damping, and we're not gonna get into detail, but that happens sometimes on the trains. Okay, there's something called, it doesn't matter. Okay, if you want, you can put it to 0 and 1. It would be perfectly correct for this class if you want. Okay, let's put this. All right, might be easier. Okay, so with that notation, we have that C over CC will be equal to what? To C, which is the one given on the equation. Okay, on the initial equation, this one over here. All right, this is the C. And the C damping, we just divided over here, will be 2m omega sub n. So we know this is equal to the new constant, C. Or from here, we can say that C times omega n will be equal to C over 2m. Okay, so why did we do all this stuff? Let's see. Page 33. Okay, so you see here C over 2m for the solution of lambda 1, lambda 2. We can write C over 2m under the function of C omega n, no? Yeah, so all this stuff just to do that. But you could keep the solution under this form, okay, and solve under this form, okay? What happens is that in most vibration textbooks is given under this form over here. All right. So substituting. So substituting, yeah, let's say here, Roman 1 into the general solution x of t So what do we have? X of t equal to C1 exponential of minus lambda 1t plus C2 exponential of minus lambda 2t. So we had lambda 1, let's do it here, was equal to C over 2m plus square root of C over 2m square minus k over m. So this can be rewritten under which form? So this could be written as C over 2m plus square root of C squared oops, sorry, let me move it. Okay, so here I did forget to put the omega n, but you can write it under this form over here. With the omega n, you can factor the omega n out. I end up with omega n factor of C plus C minus 1. Okay. Okay, so if you want, let's do it here. We have lambda 2 will be equal to C over 2m minus C over 2m squared minus K over m. We do exactly the same thing, so let's just write it down. We'll have omega sub n minus square root of omega n squared minus omega squared. So basically we get lambda 2 omega equal to omega nt of C minus 1. All right, so that the general solution can be written as what? X of t equal to C1 exponential of minus lambda 1, which is C, plus C squared minus 1 square root omega nt plus C bar 2 exponential minus C minus square root of C squared minus 1 omega nt. I mean, I'm going to give you a handout next class, or I will put on Canvas a handout with these equations. Okay, so this is the general solution again. Of free damp system. Okay, so let's see over here. All right, so if the system is undamped, what was the solution that we derived last time? Was, let's see if we can see it, was this one over here, no? C1 exponential of minus I omega nt plus C2 I positive I omega nt. All right? So this will correspond to what case? It will correspond to the case that the damping C is equal to 0. Okay? So if it's equal to 0, what are you going to have? Over here, you're going to have square root of minus 1, which is equal to I, no? So this will be equal to what? So it will be minus 1 will be I omega nt, which is the same thing as we had before, no? And here you will have, this will be minus 1, so here will be plus, so C2 exponential of I instead of minus I omega nt, which is the same thing as before. Okay? All right. So now, is what I was saying before, the solution is going to depend on what's happening with these ratios over here. I mean, with the damping, with the square root minus 1 to see if this is positive or negative. Okay, let's see what happens over there. So, if C, which defined as the damping ratio, is different than 0, which means on damp, three cases are possible. Okay, now the three cases are mentioned before: the overdamp, underdamp, or critically damp. Okay, so let's see what is the meaning of each one of them. So case one, let's say our case one will be critically damp. That means when the damping ratio is equal to 1, which basically means is 100%, no? Is the optimal value, the critical or optimal value. Case 2 will be the underdamp, which is the most common. So in that case, you have the damping ratio is lower than 1. And case 3 will be the overdamp, which is when the XC is higher than 1. Oh, so that makes me think about something. Okay, so maybe, because I always have in mind the underdamp, maybe on the page 34, when I put this is always between 1 and 2, between 0 and 1, it might not be 100% true. But what happens is that this one is the most common case, okay? So this is really for, if you want added, so it's not, this would be underdamp. All right, so I would have something a little bit wrong on the notes. All right, no wrong, but not 100% accurate. Okay, and since we're going to be solving for each one of these cases, I'm going to define now the initial conditions, so we can use the same initial condition for all three cases. So for all three cases, the following initial conditions are considered. So basically, if you remember, what do we need? Initial conditions, because in order to fully determine this solution, we need to also determine the constants C1 and C2. So if we have two constants to determine, how many initial conditions do we need? 2, no? All right, so basically, if you have two unknowns, you need two equations, all right? So the two initial conditions will be that x of t at t equals 0 will be equal to x sub naught. So let's say at t equal to 0, I displace the mass a certain distance, a constant distance, and then I will let it go from that point. And also I can say that the velocity at t equals 0, which will correspond to x dot of t at t equals 0, will be equal to a known value x sub naught, which sometimes would just be given as v sub naught. So this will be our initial conditions.